valve, such as porous plug. Its pressure decreases. Similar to liquids, gases can also be expanded. Similar to liquids and gases can also be expanded. Here we want to explain so here what is phase? First one, what it is, low temperature can be produced using substances. Low temperatures can be produced using substances that undergo endothermic phase process such as melting, sublimation, and evaporation. When high pressure liquids flow through a when high pressure liquids flows through a when a high pressure liquids flows through a substances that undergo endothermic phase process such as melting, sublimation, and evaporation. Melting, sublimation, and evaporation. When high pressure liquids flows through a turbine delivering a network output, its pressure, enthalpy, and temperature decreases. When a high pressure liquid is forced to flow through a substance. Okay, ma. Then what it is, similar to liquids, gases can also be expanded. Gases can also be expanded from high pressure to low pressure, either by using throttling, nothing but porous plug device, isenthalpic process or isothermic expansion to product to low temperatures. Whether the temperature decreases, throttling process we are discussing here, ma. It is audible. So that now what we are taking here, in general, phase transition. What is phase transition? So what is phase? Before going to phase transition, now we want to derive for phase. What is phase, ma'am? What is the Thomson coefficient? Already we discussed previously in Joule Kelvin effect. Whether the temperature decreases or increases depends on a property of the gas called Joule-Thomson coefficient. Whether the temperature decreases or increases depends on a property of the gas called Joule-Thomson coefficient. Mu J T is equal to dou T by dou P of H. The most important method of producing for producing low temperature, namely Joule-Thomson cooling. By using the process of adiabatic demagnetization, we can produce very low temperatures. By using the process of adiabatic demagnetization, we can produce very low temperatures. Phase, a form of matter that is uniform throughout in chemical composition and physical state is known as a phase. A form of matter that is uniform throughout in chemical composition and physical state is known as a phase. Example, ice, water, and steam are the three phases of a single substance. Next, phase transition. What is phase transition, ma? The spontaneous conversion of one phase into another phase is called phase transition. The spontaneous conversion of one phase into the spontaneous conversion of one phase into another phase is called as phase transition. Such phase transitions occur at a specific temperature at a given temperature. The phase transition, the added or lost Q causes the molecules of separation to change. During phase transitions, thermal energy. During phase transitions, thermal energy Q gained or lost but does not change the temperature. During phase transitions, thermal energy Q gained or lost but does not change the temperature. In general, there are two types of phase transitions. There are two types of phase transitions on the basis of heat gained. Okay, are lost and heat remains constant. These are first one. In general, there are two types of phase transitions on the basis of heat gained or lost and heat remains constant. There are first order phase transition, next one second order phase transition. First one is first order phase transition and second one is second order phase transition. In first order phase transition or first order phase change, the first one what we are discussing, the phase transition in which there is either absorbed or liberated. The phase transition in which there is either absorbed or liberated. There is either absorbed or liberated heat without any change in temperature. Is known as first order phase transition. The phase transition in which there is either absorbed or liberated. Heat without any change in temperature. Is known as first order phase transition. During first order phase change, entropy S changes discontinuously. During first order phase change, entropy S changes discontinuously. Similarly, during first order phase change, we can take a Gibbs free energy. We can change Gibbs free energy. In this, during first order phase change, what we are taken, Gibbs free energy does not change discontinuously. Example, ice converted into water. At constant temperature. Next, water converted into steam at constant temperature. Ice converted into water at constant temperature. And water converted into steam at constant temperature. Steam converted into water at constant temperature. All these are the first order phase change equations. So that was shown in the diagrams mark. That is shown in the particular diagram where we taken as pressure in y-axis and temperature on x-axis. Then curve of sublimation, curve of fusion, curve of vaporization, and the liquid state, solid state, and vapor state. Three meet at a particular point is nothing but what it is, that is a particular point. That is the triple point. Okay, all the three layers, all the three conversions meet at a particular coincidence of a point is nothing but triple point. Next, liquefaction of gas using porous plug experiment. Important. Joule-Kelvin effect or Joule-Thomson effect, both are same. Joule-Kelvin effect and Joule-Thomson effect, we can write our porous plug experiment. All these three headings we can write same only. here first P side and Q side, one side is A, one side is B, pistons we are taken. Inside inside at the center one is porous plug. The Joule-Thomson experiment involves the expansion of a gas. The Joule-Thomson experiment involves the expansion of a gas from one fixed high pressure to fixed low pressure. The Joule-Thomson experiment involves the expansion of a gas, from one fixed high pressure to fixed low pressure through porous plug under adiabatic conditions. Okay, ma. The Joule-Thomson experiment involves the expansion of a gas from one fixed high pressure to fixed low pressure through porous plug under adiabatic conditions. Here, Joule-Thomson experimental setup consists of a cylinder divided into two parts by a porous plug, consists of a cylinder divided into two parts by a porous plug. A fixed quantity of gas is contained in the cylinder by frictionless piston placed on both sides of the porous plug. Here what we are doing, ma, a fixed quantity of gas is contained in the cylinder by frictionless piston placed on both sides of the porous plug. The entire apparatus is surrounded by adiabatic valve. An entire apparatus is surrounded by adiabatic conditions and adiabatic valve only. Gas in the LHS side is maintained at high pressure. Gas at left hand side is maintained at high pressure, and in RHS side is at low pressure. Therefore, P1 greater than P2. So one side is maximum, one side is minimum, means LHS side value is maximum, means pressure value is also maximum. Therefore, P1 greater than P2. The gas is throttled through porous plug. Through porous plug from left to right while maintaining pressures P1 and P2 are constant. Suppose a fixed amount, 1 mole of gas, is passed through the porous plug. A fixed amount of gas is passed through porous plug. Thus, work involved on the LHS side is P1V1. Work involved in the RHS side is P1V1. Work involved in the RHS side is P2V2. Therefore, network involved in the system, dW is equal to P2V2 minus P1V1. So that as the process is adiabatic, dq is equal to 0. As the process is adiabatic, in adiabatic process, what it is, amount of heat will be constant. Therefore, the change in heat will be 0. Means dq is equal to 0. According to first law of thermodynamics, work involved in the LHS is P1V1. Work involved in the RHS is P2V2. Network involved in the DW system, dW is equal to P2V2 minus P1V1. According to first law of thermodynamics, dq is equal to du plus dw. So in adiabatic process, dq is equal to 0 means LHS side we are taken as 0. 0 is equal to du plus dw. Then du is equal to minus dw. Then du is equal to minus of what is dw? Minus of P2V2 minus P1V1. So U2 minus U1 is equal to P1 minus take inside means minus into minus plus P1V1 minus P2V2 avutundi. Then the difference in of internal energy U2 minus U1 LHS is equal to P1V1 minus P2V2 avutundamma. P1V1 minus P2V2 avutundi. From this we are getting the Joule-Thomson coefficient or Joule-Kelvin coefficient. U1 minus U2 is equal to P1 minus P2 ochindi. Now we are changing continuation part. U1 plus take P1V1 one side, P2V2 in one side. Then we are getting equation 1 and 2. What it is? From the above equation, LHS side minus U1 take the RHS side and minus P2V2 take this side. Then it becomes U1 plus P1V1 is equal to U2 plus P2 V2. Then U plus PV is equal to constant. U plus PV means enthalpy. H is equal to constant. Then dq is equal to du plus dq is equal to du plus dw. dq is equal to 0. Then du plus dw. dq is equal to 0 means du plus dw. Then du is equal to minus dw. du is equal to minus of what is dw? What is dw value? That is the work done in pressure and volume only, no? Therefore, du is equal to minus of P2 V2 minus of P1 V1. Then U2 minus U1 is equal to P1 V1 minus P2 V2 అవుతుంది. U2 minus U1 is equal to upper means minus of minus plus, no? Then it becomes U2 minus U1 is equal to P1 V1 minus P2 V2. Again, we can take one terms one side, one terms one side. From this equation also, we are getting same answer. Then U plus U1 plus P1 is equal to U2 plus P2 is equal to U2 plus P2 V2. Then U plus from this particular equation, we can write U plus PV is equal to constant. Nothing but H is equal to constant. Hence, the enthalpy of the gas. Hence, the enthalpy of the gas throttled through force plug. Hence, the enthalpy of the gas throttled through force plug remains constant. Hence, the enthalpy of the gas throttled through. Hence, the enthalpy of the gas throttled through force plug remains constant. Next, perfect gas. In case of perfect gas, what it is? In case of perfect gas, P1 V1 is equal to P2 V2. In case of perfect gas, P1 V1 is equal to P2 V2. From equation 1, what it is? P1 V1 is equal to P2 V2 means both sides P1 V1, P2 V2 gets cancelled. Then what we have? U1 is equal to U2. What is U1? Internal energy. Internal energy nothing but total potential energy and kinetic energy. Therefore, KE1 plus PE1 is equal to KE2 plus PE2. We know that there is no attraction force between the molecules of a perfect gas. We know that there is no attraction force between the molecules of a perfect gas. There is no attraction force between the molecules of a perfect gas. Then KE1 is equal to KE2. Then KE1 is equal to KE2. Therefore, T1 is equal to T2. T1 is equal to T2. Therefore, the Joule-Thomson effect is 0. The Joule-Thomson effect is 0 for a perfect gas. The Joule-Thomson effect. The Joule-Thomson effect is 0 for a perfect gas. Next one, real gas. For real gases, what it is? P1 V1 is equal to P2 V2. For real gases, P1 V1 is equal to P2 V2. So here it is not equal to means what it is? P2 V2 take this side. For real gases, for ideal gases, so we can condition applicable. For a perfect gas, we can take P1 V1 is equal to P2 V2. From that, we can take T1 is equal to T2. For real gases, P1 V1 is not equal to P2 V2. Hence, the net external work done. Hence, the net external work done by the gas. Hence, the net external work done by the gas. Hence, the net external work done by the gas. P2 V2 minus P1 V1 is not equal to 0. P2 V2 minus P1 V1 is not equal to 0. Therefore, there are three cases are possible. Therefore, there are three cases are possible. Depends on initial temperature of gas. Next, case 1. Below Boyle's temperature, P2 V2 greater than P1 V1. Hence, the net external work done by the gas P2 V2 minus P1 V1. P2 V2 minus P1 V1 is not equal to 0. Therefore, there are three cases are possible. Depends on initial temperature. Below Boyle's temperature, P2 V2 greater than P1 V1. Therefore, U1 greater than U2. From equation 1, what it is? So the gas shows cooling effect. Now at boils temperature, P1 V1 is equal to, at boils temperature P1 V1 is equal to P2 V2. At boils temperature P1 V1 is equal to P2 V2. Therefore U1 is equal to U2. So the temperature of the gas remains constant. Temperature of the gas remains constant. Now we are concluding to take this application continuation, ma. So U1 is equal to U2. So what we are giving here, U1 is equal to U2. So the temperature of the gas at boils temperature P1 V1 is equal to, at boils temperature P1 V1 is equal to P2 V2. That is equal to U1 is equal to U2. P1 V1 is equal to P2 V2. That equal to internal energy U1 is equal to U2. So the temperature of the gas, remains constant. Next, case 3. Above boils temperature, P1 V1 greater than P2 V2. Above boils temperature P1 V1 greater than P2 V2. Nothing but U1 less than U2. P1 V1 greater than P2 V2 means U1 less than U2. So the gas shows heating effect. Above boils temperature P1 V1 greater than P2 V2. U1 less than U2. So the gas shows heating effect. Next, Joule-Thomson cooling. For that, what we are taking, ma, consider a thermally same process, ma. Here we can take Joule-Thomson cooling. Important, this also Joule-Kelvin effect over. Now Joule-Thomson cooling, ma. Here also same structure of figure we are using. Porous plug in between, one side P1 V1, one side P2 V2 is one side is A piston, one side is B piston, P region and Q region. Consider a thermally insulated cylinder as shown in figure. Consider a thermally insulated cylinder as shown in figure. It is divided into two parts by a porous plug. And fitted with two non-conducting, divided into two parts by a porous plug and fitted with two non-conducting fissures A and B. Consider the piston A forces slowly 1 gram mole of gas. Consider a piston A forces slowly 1 gram mole of gas through the porous plug at a constant pressure P1. Hence, the gas pushes back the piston B subjected to a constant pressure P2. Let V1 and V2 be the volumes of the gas before and after passing through the porous plug respectively. Next, external work done on the gas by the piston. External work done on the gas by the piston. P1 V1 and external work done by the gas on the piston. Is P1 V1. External work done by the gas on the piston is P2 V2. Therefore, external net work done by the gas. Is equal to P2 V2 minus P1 V1. Further, an internal work is done by the gas. Further, an internal work is done by the gas to pull its molecules apart against their mutual attractions. Hence, further an internal work is done by the gas to pull its molecules apart against their mutual attractions. Hence, the internal work done, hence the internal work done by the gas is equal to integral V1 to V2 A by V square dV, integral V1 to V2 A by V square dV, A integral minus 1 by V limits V1 to V2, A integral 1 by V1 minus 1 by upper limit minus lower limit, here minus common means 1 by V1 minus 1 by V2. Then what we are getting? A by V1 minus A by V2. Okay. A is constant. Integral 1 by V square dV or integral 1 by X square dx means minus 1 by X. So in the X place we have V. Therefore, A into minus 1 by V limits V1 to V2. Now applying limits and minus is common, then you are getting A into 1 by V1 minus 1 by V2. Therefore, A by V1 minus A by V2. A by V1 minus A by V2. Therefore, total work done by the gas, total work done by the gas is equal to external work done plus internal work done. Total work done by the gas is equal to external work done plus internal work done. Therefore, W is equal to P2V2 minus P1V1 plus A by V1 minus A by V2. P2V2 minus P1V1 plus A by V1 minus A by V2. Then here what we take according to Van der Waals equation of gas, according to Van der Waals equation of gas, P plus A by V square into V minus B is equal to RT. P plus A by V square into V minus B is equal to RT avutundi. Then multiplying both the equations we have P into V, PV plus A by V square into V means VV cancel A by V minus PB minus AB by V square is equal to RT. Both the terms in LH side are multiplied. Then you are getting PV plus A by V minus PB minus AB by V square is equal to RT. So this it is clear, students. Next. So LHS, what do you have to remind ma? PV plus A by V, PV plus A by V minus PB minus AB by V square. Then on neglecting AB by V square in LHS side, AB by V square can be neglected. Then what we have ma? PV plus A by V minus PB. PV plus A by V minus PB is equal to RT. Then PV is equal to what we are taken minus PB, take that side means plus PB, plus A by V, take that side means minus A by V. Then PV is equal to RT minus A by V plus PB, which is equation number 2. Now from equation 2, P1 V1, from equation 2, P1 V1 is equal to RT minus A by V1 plus P1B. And P2 V2 is equal to RT minus A by V2 plus P2B. P2 V2 is equal to RT minus A by 2, RT minus A by V2 plus P2B. Then PV is equal PV is equal to RT minus A by V plus PB, which is equation number 2. From equations 1 and 2, what we are taken? P1 V1 is equal to RT minus A by V1 plus P1B, and P2 V2 is equal to RT minus A by V2 plus P2B. Now P2 V2 minus P1 V1 means first P2 V2 term, then P1 V1 term subtract. Then what it is ma? What is P2 V2? Plus RT minus RT cancel. Then you have minus A by 2 plus A by V1 P2B minus P1B. Minus A by V2 plus A by V1 plus P2B minus P1B. Now upper limit P2 V2 minus P1 V1 is equal to A by V1 minus A by V2. A by V1 minus A by V2 plus P2 minus P1 into B plus P2 minus P1 into B, which is equation number 3. Now substitute equation 3 in equation 1. Substitute equation 3 in equation 1. Then what it is, ma? W is equal to A by V1 minus A by V2 plus P2 minus P1 into B plus P2 minus P1 into B plus A by V1 minus A by V2. Okay, ma, substitute 3 value in equation 1. What is equation 1? P2, W is equal to P2 V2. Above we are shared, no, ma? W is equal to P2 V2 minus P1 V1 plus A by V1 minus A by V2. Now, in the place of P2 V2 minus P1 V1, you are substituting this value. Then the equation becomes A by V1 minus A by V2 plus P2 minus P1 into B plus A by V1 minus A by V2. Now, in both the terms, cancel terms cancel, then you get W is equal to 2A by B1 terms, 2A by V2 terms, then P2 minus P1 into B. Therefore, W is equal to 2 into A by V1 minus A by V2 plus P2 minus P1 into B, which is equation number 4. Now, as A by V1 and A by V2 are small quantities, as A by V1 and A by V2 are small quantities, A by V1 and A by V2 are small quantities, then A by V1 is equal to P1A by RT. A by V1 is equal to P1A by RT and A by V2 is equal to P2A by RT. A by V1 is equal to P1A by RT and A by V2 is equal to P2A by RT, which is equation number 5. Now substitute equation 5 in equation 4. Substitute equation 5 in equation 4. Then W is equal to what we are taking, 2 into P1A by RT. W is equal to 2 into P1A by RT minus P2A by RT plus P2 minus P1 into B అవుతుంది. Substitute equation 5 in equation 4. Then W is equal to 2 into, in the place of A by V1, we are substituting P1A by RT. In the place of A by V2, you are substituting P2A by RT. Then as usual term, P2 minus P1 into P. Then 2A by RT is common. 2A by RT into P1 minus P2 minus P1 minus P2 into B. Common of minus is common, then P1 minus P2 into B. Then both the terms P1 minus P2 is common, then W is equal to what we have, P1 minus P2 into 2A by RT minus B. W is equal to P1 minus P2 into 2A by RT, 2A by RT minus B, which is equation number 6. Now we know that W is equal to minus Cp dt. W is equal to minus Cp dt J, minus Cp dt J, which is equation number 7. Now substituting and comparing equations 6 and 7. LHS side is W only there. Then repeating RHS side. What is RHS side? Minus Cp dt J one side and P1 minus P2 into 2A by RT minus B another one. Then continuation of the time. Then minus Cp dt J, minus Cp dt J is equal to P1 minus P2 into minus Cp, substituting that values, then what it is, both the work terms are equal means equating that. Then you have minus Cp dt J, minus Cp dt J is equal to minus P1 minus P2 into 2A, P1 minus P2 into 2A by RT minus B, 2A by RT minus B. Then dt is equal to minus of P1 minus P2 by Cpj minus of P1 minus P2 by Cpj into 2A by RT minus B, which is equation number 8. Now equation 8 shows the expression of Joule-Thomson. Equation 8 shows the expression for Joule-Thomson cooling. Equation 8 shows the expression for Joule-Thomson cooling. Now, for a given pressure difference, cooling is inversely proportional to the initial temperature T. For a given pressure difference, cooling is inversely proportional to the initial temperature T. At any initial temperature, the cooling produced is directly proportional to the pressure difference across the porous plug. Okay, ma. At any initial temperature, the cooling produced is directly proportional to the pressure difference across the porous plug. Liquefaction of gases are liquefaction of air or regenerative cooling. Important. This is also liquefaction of gases or liquefaction of air or regenerative cooling. All the headings we can write same match. For this principle of regenerative cooling diagram is there, and liquefaction of helium is next one. These and adiabatic demagnetization, all these are important in a low temperature physics. Principle of refrigeration, principle of regenerative cooling, adiabatic demagnetization, liquefaction of helium. These are very, very important. Next class, we discuss quantum theory of radiation. In this class, we complete these topics. In general, liquefaction of gases or liquefaction of air or regenerative cooling, we can take in general, there are two methods by which gases may be liquefied. In general, there are two methods by which gases may be liquefied. These are: first one, the gases are sufficiently cooled. The gases are sufficiently cooled and simultaneously subjected to a the gases are sufficiently cooled and simultaneously subjected to a high pressure. The gases are sufficiently cooled and simultaneously subjected to a high pressure means Joule-Thomson effect. The gases are sufficiently cooled and simultaneously subjected to a high pressure. Joule-Thomson effect. Next, cooling the gas below its critical temperature. And then applying sufficiently high pressure. Regenerative cooling. Next, principle of regenerative cooling. Here, what we are taking air at heat exchanger, water, and air at 1 atmosphere. All this we are discussing in this diagram. Principle of regenerative cooling. In this, when a compressed gas initially below its temperature of inversion, is forced through a nozzle, its temperature falls. It is known as Joule-Thomson effect. When a compressed gas initially below its temperature of inversion is forced through a nozzle, its temperature falls. Is forced through Okay. Now liquefaction of gases. We discussed technical issue. Okay. Here, when a compressed gas initially below its temperature of inversion, it forces to a nozzle. Its temperature falls. It is known as Joule-Thomson effect. It is known as Joule-Thomson effect. The fall in temperature increases. The fall in temperature increases as the initial temperature of the gas. The fall in temperature increases as the initial temperature of the gas is decreased. In this regenerative cooling process, the gas which has been suffered in this regenerative cooling process, the gas which has been suffered Joule-Thomson expansion. Joule-Thomson expansion is made of to flow back over the tube containing the incoming gas. The regenerative cooling process. The regenerative cooling process is achieved by the arrangement as shown in figure. It contains mainly two parts, namely compressor P and heat exchanger H. Pure and dry air is compressed by compressor P, and the heat of compression is removed by flowing water in a jacket surrounding by a portion of the tube. Okay, ma. In this regenerative cooling process, the gas which has been suffered Joule-Thomson expansion is made to flow back over the tube containing the incoming gas. The regenerative cooling process is achieved by the regenerative cooling process. The gas which has been suffered Joule-Thomson expansion is made to flow back over the tube containing the incoming gas. The regenerative cooling process is achieved by the arrangement as shown in figure. It contains mainly two parts, namely compressor P and heat exchanger H. Pure and dry air is compressed by compressor P. Pure and dry air is compressed by compressor P, and the heat of compression is removed by flowing water in a jacket surrounding a portion of the tube. Further, the gases flow through the tube. Which surrounded by heat exchanger, and reaches the nozzle and due to Joule Kelvin effect the gas is cooled. This cooled gas cools the incoming gas. As a result, the incoming gas is cooled. And again suffering the Joule Kelvin effect. Becomes still more cold. And again suffering the Joule Kelvin effect becomes still more cold. In this way, the outgoing cool gas cools the in this way, the outgoing cold gas cools the incoming gas, and cooling due to Joule Kelvin expansion increases at each successive expansion. By continuing this process, ultimately a temperature is reached. By continuing this process, ultimately a temperature is reached at which the gas is liquefied. This is known as principle of regenerative cooling. Okay. Next, liquefaction of helium or Kapitja's method. here. What it is? Helium was the last gas to be liquefied. Helium was the last gas to be liquefied. Actually, the liquefaction of helium is very difficult. The liquefaction of helium is very difficult because its inversion temperature Ti is 33 K and critical temperature Tc is 5 K. Such values are very low. Even though Kapitja was liquefies the helium, even though Kapitja was liquefies the helium by using the combined method of external work, doing in an adiabatic expansion, and Joule-Thomson effect. Helium was the last gas to be liquefied, and even though Kapitja was liquefies the helium by using the combined method of external work done in a adiabatic expansion and Joule-Thomson effect. The experimental arrangement of Kapitja method shown in figure ma, it contains mainly four parts. Named as compressor P, compressor P, uh, liquid nitrogen bath, and N, heat exchanger H, and expansion engine E. Initially, a pure and dry helium is taken in the cylinder piston arrangement. And is compressed to 30 atmospheres by compressor piston. P. Heat of compression is removed by flowing water. Heat of compression is removed by flowing water in a jacket surrounding portion of the tube. surrounding portion of the tube. The gas is then pre-cooled. The gas is then pre-cooled by passing it through a bath of liquid nitrogen boiling under reduced pressure. The pre-cooled gas is divided into two parts at A in the heat exchanger H. One part passes on the expansion engine E. Due to adiabatic expansion of the gas, it cools to minus 263 degrees centigrade. This cooled gas rises up in the heat exchanger. And cools the second part coming towards the nozzle, and the second part is now so cold. That after the expansion at nozzle, and it is liquefied at a temperature minus 268 degrees centigrade or about 5 Kelvin. The liquefied portion is collected in Devar flask, and the remaining part goes back. The liquefied portion is collected in Devar flask, and the remaining part goes back to the compressor through heat exchanger. That is the liquefaction of helium. Next one, adiabatic demagnetization or magnetic refrigeration. Demagnetization is based on adiabatic demagnetization